Good day to all. We are from Group 1 and Group 2, and my group members are KRISNAVENII, SITI HAMIDAH, and Mitan Faizi, No Arif Ikhwan, Chong Teng, Tan Boon Chu, and Uncle Wei. Today we will present on gradient descent. So for the definition, gradient descent is an iterative first-order optimization algorithm used to find a local minimum or maximum of a given function. This method is commonly used in machine learning and also deep learning to minimize a cost or loss function. It is used when training data models can be combined with every algorithm and it is easy to understand and implement. As we can see in the diagram, that one is example of gradient descent, which usually we can plot it using Weka or any tools. And gradient descent is best used when the parameters cannot be calculated analytically and must be searched for by an optimization algorithm. So there are three types of gradient descent. The first one is batch gradient descent. Batch gradient descent sums the errors for every point in a training set, updating the model only after all training examples have been evaluated. This process referred to as a training epoch. Like CNN, we have a few epoch. Batch gradient descent also usually produces a stable error gradient and convergence, but sometimes that convergence point isn't the most ideal, finding the local minimum versus the global one. Batch gradient descent performs redundant gradient computation as it recompute gradient for similar examples. So for the second type is stochastic gradient descent. We call it as SGD, runs as a training epoch for each example within the dataset, and it updates each training example parameter one at a time. Since you only need to hold one training example, they are more easy to save in memory compared to the first method, which is batch. SGD will not create a redundant result, while these frequent updates can offer more details and speed. So compared to batch, SGD is more faster to batch. Its frequent updates can result in noisy gradients, but this can also be helpful in escaping the local minimum and finding the global one. So for the third type, which is mini batch gradient descent, mini batch gradient descent combine concepts from both the first method and the second method that I explained just now, and it splits the data set into small batch size and perform updates on each of those batches. This approach strikes a balance between the computational efficiency of batch gradient descent and the speed of stochastic gradient descent. So the advantages of mini batch, which are the first one is to reduce the variance of the update, which can lead to more stable convergence. And the second advantage is it can make use of highly optimized metrics calculated commonly found in the state-of-the-art deep learning libraries. As we can see in the diagram, there are three types of descent that I explained just now, and we can see the pattern for the batch gradient is a straight line, a linear line. It means that it will be form a redundant result compared to stochastic gradient descent. The pattern is up down. It will not form a redundant result. And the mini batch is a combination of these two methods, and it form a middle line. So um, stochastic gradient descent is faster than batch gradient descent, and the best and the ideal method to conduct the gradient descent actually is a mini batch gradient descent, which combine between these two methods. So next, I will pass to my next teammate to explain on calculation of gradient descent.
Okay, I'm Ikhwan and I'm going to explain for the calculation of the function requirements. The gradient descent algorithm is not applicable to our function because there are three unique prerequisites. A function must include differentiable and convex. A differentiable function has a derivative at each point and in each domain, whereas non-differentiable function typically contain a step, a curve, or a discontinuity. And we can observe based on the diagram, which is the example of differentiable function. and the non-differentiable function. Okay, next. Okay, the function must be a convex. This means for an invariant function, the line segment connecting two function point lies on both its curve and it does not cross it. This condition is stated mathematically for 2 points x1, x2 on the function curve as f divided by lambda x1 plus 1 minus lambda x2 is less than lambda f x1 plus 1 minus lambda f x2. The lambda represents the location of a point on a section line, and the value must be between 0 to the left point and 1 to the right point. And if the example of lambda equal to 0.1 means it's in the middle. As you can see, this is the example of the convex and non-convex function. Okay, next. Okay, the another method for determining whether an unvariable function is convex is to compute the second derivative and see its value is always greater than 0. As we can see from the formula, d squared fx divided by dx squared is greater than 0. A gradient descent approach can also be used with quasi-convex functions. However, they frequently feature so-called saddle points, or also known as minimax points, where the algorithm can become stuck, and we will demonstrate. And the following is an example of a quasi-convex function. This is the fx equal to x4 minus 2x cubed plus 2. And below is the function of the quasi-convex function as well, the formula. Okay, next. Okay, now for the calculation for the gradient, it's just the first derivative at the given position for a variable function, and it is a vector of derivatives in each primary direction in the case of multivariate function along the variable axis, because we are only interested in slope along one axis and not in the others, and these derivatives are known as partial derivatives. The following is the definition of the gradient for an n-dimensional function fx at a given point P. So we can see it's in the formula. So the upside down triangle is a nabla symbol, or also read as del, and after that calculation can be made for an example two-dimensional function. And below, to better understand how to do it, is fx equal to 0.5x squared plus y squared. So let us say we are interested in the gradient at point P 10 and 10. So basically this diagram is the 3D plot of which we want to calculate. So this is the formula. So after that we use the formula that includes the nambla symbol. Okay, and because of this value, we can conclude that the slope is twice as steep along the y-axis. Okay, next I will pass to my other team members.
For the example of gradient descent, first is a quadratic function. First, let's take a simple quadratic function as defined as, which is fx equals to x squared minus 4x plus 1. Because it is an univariate function, a gradient function is needed, which is dfx over dx equals to 2x minus 4. The functions are written in Python as shown in the picture below. For this function, by taking a learning rate of 0.1 and starting point at x equals to 9, we can calculate each step by hand. The first 3 steps are shown as below in the picture. Next. The Python function to call this function is shown in the image. History, result equals to gradient underscore descent, 9 gradient function 1, 0.1 and 100. The image below shows the steps taken by the gradient, the first 10 steps taken by the gradient descent algorithm for learning rate of 0.1 and 0.8. From this image, we can see that for the smaller learning rate, as the algorithm approaches the minimum, the steps are getting gradually smaller. For a bigger learning rate, it is jumping from one side to another before converging. In the image, in the left side of the graph shows the learning rate for 0.1 and the right side of the graph shows the learning rate of 0.8. Next I pass to the next team member.
So for the example of coding, I would like to introduce with a simple question. which is to find the local minima of the function y equal to x plus 5 to the power of 2, starting from the point x equal to 3, as shown in the figure here. As you can see from the figure, the answer is clearly negative 5. So by using gradient descent, there are a few steps we need to take into account. The first step is to initialize x equal to 3. Then find the gradient of the function dy dx, which is the derivative of the y function, equal to 2 multiplied by x plus 5. And for the step 2, move in the direction of the negative of the gradient. Assume learning rate is 0.01. And for step 3, perform iteration of gradient descent. And the final step, step 4, we can observe that the x value is slowly decreasing and should converge to negative 5, which is the solution. So next slide, I'll pass to Audrey to explain about the formula and the step 1 coding.
Okay, so for the formula for this question, there has local minima of function y. So from the formula at the left hand side, you can see the initial parameters that we have set the s not equal to 3 as the mentioned in the question, and the running rate we have set here is 0.01, and the function y has been differentiated into for the carry on, and the iteration function that you can see the formula, the S1 is equal to the S0 that I have calculated previously minus the learning rate times with the differentiate function. So the following iteration 2 also will be doing the same step by plus the previous iteration result and minus with the learning rate times with the function. And from the gradient descent in the Python, you can see the first one, we have initialized the parameters with the number 3 of the s point started and the rate into 0.01. The precision we have set into 0.0401, which has to use to stop the algorithm learning precision, and the previous step size equal to 1 we have set up, and the maximum iteration we will set up to 10,000, and the iteration with the initial rate 0 and the differentiation lambda function argument is set to the differentiation y of function s equal to the 2 times s plus 5 for our gradient function. So for the next, I will present the step 2.
Hello, the step 2 is about a loop to perform the gradient descent. The loop will stop when the difference between two values from the consecutive iteration, which is less than the precision value, or the number of iterations exceeded 10,000. So the while loop is used, and the condition mentioned is in previous one is set as the condition for this while loop, and then it will store the current x value in the previous x value, and then for the current x value, it will equals to the current x value minus the learning rate times the gradient of the previous x value, and then the previous set size is the absolute value of the current x value minus the previous x value. The iteration number will be increased by 1, and each of the iteration number will be printed with the current x value. And finally, it will print the final current x value at the end of the coding. So next. So the iteration 1 is taking the x0 minus the learning rate times the gradient, and for the iteration 2, it will take the value of x1 minus learning rate times the gradient. And on the right, it will showing the iteration 1 starting with the x value 2.84 until next. Until finally the iteration will stop at the iteration of 595 at the value of x equals to negative 5, which is also shown in the graph. So these are the references for our topic. Thank you.